Okay, so we're gonna go over the last three examples here. So example number 3, 1.5 joule is stored in a spring. So 1.5 of energy stored in a spring. Is if the spring constant is 5 Newton per meter, how far is the spring compressed? So how far? So that constitutes a displacement, right? So that would be your x. That's a question mark. So again, it would be advisable to write the given and the unknown. So you have given stored in a spring, so we use E sub S. So that's 1.5 joules. The K is 5.0 Newton per meter. And then X would be the question mark. Okay, so now for my solution, so E sub S is given, so might as well, maybe my starting equation is the equation for the elastic energy. So if you can see, everything is given except for X. So therefore, this particular equation is enough for me to solve for my value of X. So what you can do here is either you substitute first. So that means that I have 1.5 joules for my E sub S. So I substitute that one first, and then the value of K is 5. So my K, so that would be 5. And then X squared, I don't know that one, over 2. So I can multiply 2 on both sides. The purpose of that one is that I want to get rid of my denominator 2. So this is 3 is equal to 5x squared. And to solve for x, I need to isolate my x. Still have to divide both sides by 5. So this gives me 3 over 5 is equal to x squared. But to solve for x, I'm going to take the square root of both sides to get the value of x. And the value of x would be 3 divided by 5, and then you take the square root of that. So in two significant digits, that would be 0.77 meters. So the unit is automatically in meters. Okay, so I would expect that the final answer must be in meters, because everything, the energy is in joule, and the spring constant is in Newton per meter. Okay. Okay, example number 4. You're given here that a spring has a spring constant of 56 Newton per meter. How much potential energy will it store when stretched vertically by hanging 2 kilograms from its end? So let's try to examine what are the things that is given to me. So we have the spring constant, and then I'm just given the mass that is hung to that particular spring, and then I am asked to solve for the potential energy. So therefore, this is my ES. So potential energy. Static. No, not static potential energy, but spring energy stored in the spring, or elastic potential energy. So how do we answer this particular question? Well, let's try to identify first the things that we have. So let's try to write our given. So we're given the value of K, that's 56 Newton per meter. And then we're just given the mass. Okay, the mass is 2.0 kilograms. And then, well, we actually don't know X. And the main question is your ES. Okay, the energy stored in your spring. You have two unknowns. Well, let's try to see, since we want to solve for E sub S. So I'm gonna start with that solution. So I'm gonna start with that equation. E sub S is equal to kx squared over 2. Okay, so if you can see here, well, S is a question mark as well as your X. Remember that the main question here is the potential energy. So therefore, we want to solve for this. So this is our main question. But in order for us to solve for E sub S, the elastic potential energy, we need to know what would be the value of X. It's not given in the problem, right? So if you can see, there's no distance there. So therefore, you need to solve for X first. Okay, so I need to solve for the value of X. So I need to solve for the value of X first. But how would I do that? Okay, so remember that that would be the displacement. X would be the displacement from its equilibrium position. So we actually need some help of what we learned in our dynamics. So let's say in a spring. So let's say originally this is your spring. Okay, you didn't attach anything, so that would be case. But if you're gonna attach something, so this spring will be stretched out. So maybe perhaps it will something like that. So if you're gonna place, this is your object. So this is the mass. M is equal to 2 kilograms. Okay. So it will stretch out. This one here, the one on the right, this is without mass attached. Okay. The other one is with a particular mass. So actually, if you're gonna read, so this would be your X here. Somehow the displacement. So, or maybe I'm just gonna say I'm gonna use this part here as the basis for, yeah. So that would be my X, because it is now originally without the mass. So the form of your spring is something like this. So now with the mass, it gives you like this. Now I think it helps that we're given the mass of the one that is hang in our object. This one here, the mass, it's given there. Use the blue. So, oops. So we're given this mass here. So if I gonna draw the free body diagram of M, so if I gonna draw, what would be the free body diagram of M? Okay. of the object attached. Well, remember that this particular object doesn't move. So there are two forces acting on M in this particular case. One is Fg, and the other one would be your Fs, or the force exerted by the spring. It would be upward. And since there's no movement, this doesn't move, so this is in equilibrium, it is at rest. So since M does not move, since M is at rest, I'll just use at rest. At rest, summation of all the forces on M is equal to 0. So that means that the magnitude of my spring force is equivalent to the magnitude of my weight. So that means that these two have the same value. Okay. Okay. Oops. Okay. So if you can see here, again, when you attach the mass on the spring will stretch downward. Okay. So when that happens, if you can see, now the mass is acted upon by two forces. One would be downward, which is equivalent to the weight of the object. The other one, since it is attached to the spring, the upward force is the force exerted by the spring, and that is your Fs. So therefore, the force exerted by the spring, the amount of force exerted by the spring is the same amount to the force of gravity. So therefore, Fs is just equivalent to Fg. So knowing that one, that Fs just equivalent to Fg, so that is mg, mass times acceleration due to gravity. So knowing that one, we can use Hooke's law. Remember, Hooke's law is Fs is just equivalent to kx. So again, this is from Hooke's law. Okay, so Fs is just equivalent to kx. But the magnitude, remember when we try to define that one, that is just the magnitude. So the magnitude of your Fs, noting this one here, is just equivalent to mg. So this is just mg. So mg is equal to kx. But if you can see, mass, g is just a constant, and k is also given. So therefore, you can solve for x. X is just equal to mg over k. So that would give me 2 times 9.8 divided by k of 56. So therefore, x is equal to, so I'm just gonna multiply my 9.8 with 2 and then divide it with 56. So that's around 0.35. So it should move. So therefore, this particular distance here is 0.35 meters. So now you have your x. Okay, the value of x is equal to this. So you can use that one to solve for the stored energy by the spring. So K is 56 times 0.35 squared divided by 2, and then that should give you an answer of, so 0.35 squared times 56 divided by 2. So the answer should be 3.4 joules. So the energy stored in your spring is given as 3.4 joules. So any question with this one here? Anyone? Any questions? No.
Mr. Villian?
Yes.
On like a test or something, will we have to write any like free body diagrams?
Well, if it helps, yeah. But like for example, in this case, without seeing the free body diagram, I think it's very hard to see that your Fs is equivalent to Fg. Again, you go back to your dynamics here, that since this is not moving, the net force is equal to 0. But if you can see what are the forces acting on your mass, well, there are only two: the weight of the object, or the gravity, Earth's pulling the object down, and the spring going up. Although if you can somehow see that one, that indeed the spring force is just equivalent to the weight of the object, well, yeah, but it's not a particular problem that you're gonna get the solution right away. So for example, in this case, if you can see, you need to solve first for x, because at the start, so it's a good thing again if you see the given and then you started with your solution. So this is always the case. Whatever is being asked in the question, you always start with the equation that will solve that particular unknown, or for that particular quantity. So I started with E sub S because the question is how much potential energy. But then again, looking at my equation, well, I need to solve for X. That's why I need to find a way to solve for X. Okay?
Okay, thank you.
You're welcome. So any other? Okay, so we move on to example number 5. So bungee cord. So, well, a bungee cord is works the same as a spring because it can stretch out. So there must be, in stretching it out, there's an elastic potential energy there. So this is same thing with, yeah, string in a bow and arrow. So you're actually using the elastic potential energy of your bow there, the string of the bow, to make your arrow move or fly. So a bungee cord is stretched 2.5 beyond its equilibrium position. So for letter A, how much energy stored does the core have? And then assuming that all stored elastic potential energy is converted to kinetic energy, what is the maximum speed that a person, so 50 kilograms, so that means that there must be a recoil. I don't know who have done, well, I haven't done, and I don't know. I don't know if I can try bungee jumping, but yeah, I think maybe not at my age. Okay, I'm no longer that adventurous. But anyway, so if it's stretched out, you will be actually going upward because there's stored energy with that. So and then you can convert that stored energy to kinetic energy. So that's why you will move back up. Okay, so let's try to answer this question here. So generally, you're given by the following. You're given K as 150 Newton per meter. And then well, this would be your x 2.5 meters. Explicitly said that it's beyond the equilibrium position. That means that uh, you you're stretching out by that much, 2.5 meters. So for letter A, we need to solve for the energy stored in the spring. So again, since the question is energy stored, so we try to start with the equation. So E sub s, it's kx squared divided by 2. And well, it's very convenient because everything is given from the question already. So all we need to do is just substitute that one. 150 multiplied by 2.5, then squared over 2. So energy stored in a spring in that bungee cord is 150 multiplied by 2.5 times 2.5 divided by 2 into significant digits, that's 470 joules. So this is the energy stored in that. So for letter B, it says that assuming, although this is in reality, this is hardly the case, is converted to kinetic. So all of your elastic energy is converted to kinetic energy. What would be the maximum speed of the person? So remember that the person will move back up. Well, in a bungee, if you're doing the bungee jump, you're gonna go up, back up because of the elastic energy stored in that particular cord. Okay, but assuming all of that elastic potential energy is converted to kinetic, so what is the maximum speed? So how fast will you be moving, or the person is moving? So again, we're given here that m is equal to 50.0 kilograms, and again it says that es is just equivalent to your e sub k. Okay, and then we're being asked to solve for v. So in this particular case, well, since the elastic potential energy is equivalent to kinetic energy, so that means that this value here is the same as the value here. So the kinetic energy. So if this is 470, so if that is 470, that means that my kinetic energy is 470 also. Okay, so even though indirectly I was not given the value of kinetic energy, but since in the problem it says that all of your, so maybe just that kinetic or your stored energy is converted to kinetic, so I can assume that the kinetic energy is equivalent to 470. So since I'm solving for V, and if you can see, even though I've given E sub S there, but E sub S doesn't constitute speed, but it is in the equation of your kinetic energy. So therefore, I'm going to start with my kinetic energy equation, which gives me mv squared over 2. So if you can see, kinetic energy is given, well, that's already given there. The mass is also given in the problem. So the only unknown is the speed, or v, the how fast, it describes how fast it'll be moving. Okay, so therefore this particular equation is enough for me to solve for the speed. So it's either you substitute first, so 470 is equal to 50 v squared over 2. So you can do times 2 times 2 So this gives me 0, clinker 1, so 940, 50 V squared over 50 over 50. So that's around V squared is equal to 94 divided by 5, that's 18.8. And then I'm gonna take the square root of both sides. So V is equal to, oops, it's around 4.3. So that would be around 4.3 meters per second. Okay, so maybe this is now the recoil. You'll be moving that fast. Okay, once all of that potential energy is converted to kinetic, so you'll be moving 4.3 meters per second.